Some of the most advanced materials ever created were forged centuries ago. These are the lost metals and alloys, substances with properties that our modern laboratories still cannot replicate. We are going on a journey to uncover these forgotten marvels, from the watery patterned blades of Damascus Steel to the legendary Orichalcum of Atlantis. You will discover why entire branches of ancient technology have vanished, leaving behind artifacts that are both brilliant and baffling. How did a Roman cup change color with the light? And what was the secret ingredient that made their concrete last for millennia? By the end, you will see human history not as a straight line of progress, but as a story filled with profound and permanent losses. What does it truly mean for knowledge to be lost forever? A master bladesmith heats a bar of the finest modern steel in a blazing forge. With precision hammers and hydraulic presses, he painstakingly shapes it, trying to mimic the legendary curves of a Damascus sword. He etches the surface, hoping to reveal the distinctive watery patterns. The result is a beautiful blade, to be sure, but it is not the same. The pattern is superficial, a mere decoration. The legendary edge that could slice a falling silk scarf and still shatter a knight's broadsword remains elusive. This is the core of our mystery. We live in an age of microscopic analysis and atomic manipulation, yet we cannot reverse engineer what artisans achieved centuries ago. This failure forces us to reconsider everything we think we know about technological progress. It suggests that our ancestors did not simply stumble upon these wonders. They walked a different technological path altogether, one built on deep, empirical knowledge that was never written down. These lost metals are not merely forgotten recipes. They represent entire schools of thought, complete systems of making that have vanished from the earth. When a historian holds a piece of Roman concrete that has endured for 2,000 years, while our own structures crumble after decades, they are not just holding a material. They are holding a question. The true loss is not the metal itself, but the human ingenuity that conceived it. These artifacts stand as permanent reminders that history is not a straight, ascending line. It is a story with detours and dead ends, with entire libraries of practical wisdom that have been permanently erased. That beautiful, modern imitation of a Damascus blade holds the key to a deeper puzzle. What does it actually mean for a technology to be lost? It is not simply a matter of a single, forgotten ingredient, like a missing line from a recipe. True loss is far more profound. It is the disappearance of an entire ecosystem of knowledge. This includes the specific, often unrecorded source of the raw materials, the unique and subtle conditions of the manufacturing process, and most elusively, the tacit skills of the artisan. Tacit knowledge is the kind of understanding that lives in the hands and the eyes, not in a book. It is the feel of the steel at the exact right temperature, the specific rhythm of the hammer strikes, the intuitive adjustments made in the moment that no manual could ever hope to capture. Think of a master chef's most famous dish. You might have the complete list of ingredients and the step-by-step instructions, but without the chef's lifetime of experience, can you truly replicate the texture, the aroma, the perfect balance of flavors? You might create a good meal, but not the legendary one. This is the chasm we face with these ancient metals. Modern science can give us a perfect chemical breakdown of a piece of Damascus steel or Roman concrete. We know what atoms are there, but we do not know the dance. We do not possess the generations of accumulated, hands-on wisdom that guided every step of its creation. The real secret was not just in the formula, it was in the fingertips of the master, a living library of technique that closed its doors forever when the last practitioner died. This is a sobering reality as we try to resurrect these marvels. We are trying to read a book where the most important chapters were never written down. That living library of a master's touch was only one part of the recipe. Another crucial chapter was written across the landscape itself, in the very dirt and rock from which these materials were born. The unique composition of many lost alloys depended on ores sourced from ancient trade networks that have long since vanished from the world. These were not just any materials. They were materials with a specific, unwritten signature. A legendary blue glass from ancient Egypt, for instance, might owe its otherworldly hue to a trace amount of cobalt that could only be found in a single, now depleted deposit deep in the Persian desert. The secret to a metal's legendary flexibility might have been a minuscule amount of tungsten that traveled thousands of miles along forgotten caravan routes. The artisans who worked these materials may not have even known the scientific reason these particular ores were superior. They only knew that the raw iron from one specific valley or the sand from a certain riverbed produced results that nothing else could match. Their entire craft was built upon a fragile, global supply chain that they themselves could not see. Then empires fell. Trade routes were severed by war, climate change, or simply the slow unraveling of civilization. The knowledge of where to find those special ores died with the merchants who traveled those paths. The mines themselves were exhausted, or their locations were lost to time, overgrown by jungle or buried by desert sands. So when we try to recreate these alloys today, we face a geographical ghost. We can analyze a sliver of Damascus steel and identify trace elements like vanadium, but we cannot find the original iron ore deposit that naturally contained them in that perfect, subtle balance. Our search for the ingredients is a hunt for a phantom on a map that no longer exists. This reveals a profound truth. The loss of these metals is sometimes not a failure of our chemistry, but a loss of place. It is an economic and geographical mystery where the very earth that gave birth to these wonders has closed the door behind it. The legend of these swords begins with a story that terrified European knights. Crusaders returning from the Holy Land told tales of Saracen warriors wielding blades of unthinkable sharpness. They claimed a Damascus sword could be thrown into the air and sliced through a floating silk scarf as it fell, and then, in the very next moment, cleave a knight's helmet and the skull beneath it without losing its edge. This was not mere exaggeration. It was a genuine technological shock, a confrontation with a material science that seemed to border on magic. The secret of this legendary metal was not born in Damascus itself, but began its journey far to the east in the furnaces of India. There, artisans created the raw material known as Wootz steel. This was a high-carbon steel ingot produced through a unique and precise smelting process in small, sealed crucibles. But the Wootz ingot was just the beginning. The true miracle happened in the hands of the Damascene smiths. Through a painstaking and secret forging technique, involving repeated heating, hammering, and a very specific cooling cycle, they transformed that raw ingot into the patterned blade of legend. The beautiful, watery design was not etched on for decoration. It was a visual map of the steel's incredible internal microstructure. For centuries, this structure was a complete mystery. It is only with the advent of modern electron microscopes that we have been able to peer into the heart of a genuine Damascus blade. What scientists found was astonishing. The steel contains carbon nanotubes, structures we consider a marvel of modern nanotechnology. These tiny tubes, along with nanowires of cementite, an extremely hard iron-carbon mineral, are woven into the metal's very fabric. This complex nanostructure is what gave the sword its paradoxical combination of a razor-sharp, resilient edge that resisted chipping, and a flexibility that prevented it from shattering on impact. Modern metallurgists can see this structure, they can identify the chemical recipe, and yet they cannot reliably recreate the exact process that forged it. The quest is not merely to make a hard sword, it is to understand and command the alchemy that could weave nanotechnology into steel, using only a forge, a hammer, and an artisan's profound, unwritten knowledge. That intricate dance of heat and time began with a raw material as mysterious as the finished blade. The Wootz steel ingot, forged in the crucibles of southern India, was itself a masterpiece of ancient metallurgy. Artisans would pack iron along with specific organic materials like wood or leaves into a small, sealed clay pot. This crucible was then heated for hours, not in a massive open furnace, but in a carefully controlled fire. The sealed environment was crucial. It prevented the iron from burning and instead allowed it to absorb a high amount of carbon from the organic matter, transforming it into a unique form of high-carbon steel. But the real magic happened after the heating. The smiths did not quench the glowing crucible in water. Instead, they allowed it to cool down super slowly over many hours, sometimes even an entire day. This patient, deliberate cooling was not a passive wait. It was an active part of the process, a critical phase where the internal structure of the steel was being written. As the ingot cooled at this precise, glacial pace, the carbon within it could not remain dissolved. It began to precipitate out, forming microscopic clusters and chains. These carbon-rich areas would later, under the hammer of the Damascus smith, become the hard cementite nanowires, while the softer steel around them formed the flowing, watery pattern. Modern analysis has pinpointed trace elements like vanadium in the original Wootz, which likely acted as catalysts, helping to control the formation of these carbon structures. Yet, knowing the ingredients is not enough. We struggle to reproduce the exact thermal cycles, the subtle variations in the atmosphere inside that sealed clay pot, the specific quality of the heat from a charcoal fire that breathes and flickers differently from our electric furnaces. The ancient smiths were not just following a recipe, they were reading the fire, feeling the time, and conducting a delicate thermal symphony. We have the sheet music, but we are still learning to hear the music itself. While the smiths of Damascus perfected their steel, another civilization was mastering a weapon of pure terror on the high seas. Imagine the horror of a sailor in the 7th century, watching an enemy ship draw near. A strange tube projects from its bow, and then, with a roar and a whoosh, a stream of liquid fire arcs across the water. It is not ordinary fire. This substance clings to everything it touches, to wood, to sails, and most frighteningly, to the water itself. It cannot be doused with water. In fact, water only makes it rage more fiercely. This was Greek fire, the Byzantine Empire's ultimate naval weapon, and its exact formula is a secret that perished with the empire that guarded it so fiercely. The descriptions from history are clear and terrifying. This incendiary liquid was projected from pressurized siphons, allowing it to be sprayed in a continuous, fiery stream that could engulf an entire vessel in minutes. It burned on the surface of the sea, creating a wall of flame that could break any naval formation. For 700 years, this technological marvel helped defend the walls of Constantinople, repelling one siege after another and preserving the heart of the Eastern Roman Empire. Its secrecy was a matter of national survival. The formula was a state secret, known only to a handful of individuals, perhaps even only to the reigning emperor and one specific family of artisans. They carried this knowledge as a sacred trust, and they took it with them to the grave. Modern chemists have their theories, of course. The base was likely naphtha, a form of crude oil, which would explain how it floated and burned on water. Some accounts suggest the addition of quicklime, a substance that heats up spontaneously when it contacts water, which could have helped ignite the mixture. Others propose secret thickeners like resin or wax to help it cling to targets, or even other chemicals that created a fire so hot it could melt through armor. We have tried to recreate it. We have mixed these ingredients, but the results are always a pale shadow of the historical terror. Our mixtures burn, but they do not possess that legendary, unquenchable quality. They do not stick and spread with the same tenacious fury. The failure tells us that the secret was not just in the ingredients list, but in the precise proportions, the specific grades of naphtha, the exact method of preparation and pressurization. The loss of Greek fire represents more than just a missing recipe. It was a catastrophic failure in the transmission of military technology. This was a weapon so potent, so decisive, that its possession could have rewritten the map of Europe and the Middle East for centuries to come. Its formula remains one of history's most fiercely guarded secrets, not because it is still protected, but because the knowledge itself has simply vanished from the world. The challenge of recreating Greek fire is not a simple lack of ingredients, but a profound chemical puzzle. Modern pyrotechnics give us napalm, which burns intensely, but it can be extinguished with enough water. We have white phosphorus, which ignites in air, yet it does not float and burn on the sea. The Byzantine weapon defied these limitations. Its core mystery lies in a substance that performed 3 seemingly impossible acts at once. It had to ignite reliably, often on contact with water. It then needed to float, clinging to the waves rather than sinking beneath them. And finally, it had to burn with such ferocity that water became a fuel instead of a cure. Think of trying to light a puddle of gasoline on the surface of a lake. It would blaze, but only briefly, and a large wave could easily smother it. Greek fire behaved as if the very water was part of its recipe. Chemists theorize the base was a form of light crude oil or naphtha, which is naturally buoyant. But to achieve that unquenchable quality, the mixture almost certainly contained an oxidizing agent like saltpeter, which provides its own oxygen to sustain combustion. The real secret, however, may have been a third, unknown component. Perhaps it was quicklime, which reacts exothermically with water, generating immense heat that could instantly ignite the petroleum mixture. Or maybe it was a different, lost catalyst that created a gel-like substance, allowing it to adhere to surfaces and burn longer. Our modern attempts produce flammable liquids, but they lack that terrifying, self-sustaining reaction. The ancient chemists were not just mixing chemicals, they were orchestrating a precise dance of reactivity. They understood practical chemistry on an intuitive level that our analyzed formulas struggle to capture. The fire may be gone, but the mystery of how they commanded the sea itself to burn continues to challenge our understanding of the past. While the secret of Greek fire vanished in flame and smoke, another ancient marvel stands in silent, stony defiance. Roman harbors, submerged in the corrosive sea for 2,000 years, remain almost perfectly intact. Their modern counterparts, built with our advanced concrete, often crumble into useless rubble after just 50 years. This is not a minor difference in durability. It is a monumental failure of our own material science, a quiet rebuke cast in stone by a civilization that perfected a recipe we have forgotten. The secret to this longevity lies not in a single, mysterious element, but in a chemical reaction the Romans engineered by accident, a process that makes their concrete not a static material, but a living one. They mixed a specific volcanic ash known as pozzolana with lime and, crucially, seawater. This was the catalyst. When seawater infiltrates the concrete, it reacts with the pozzolana and lime in a slow, continuous process. Over decades and centuries, this reaction grows tiny, interlocking crystals of a mineral called aluminous tobermorite. These crystals are incredibly strong and stable. They act as a reinforcing skeleton within the concrete, blocking the growth of microcracks that would spell the end for modern structures. Even more astonishing, if a crack does begin to form, the incoming seawater can trigger the formation of new crystals, effectively healing the wound. Our modern concrete does the opposite. It is designed to resist water, but when water eventually seeps in, it reacts with internal components to form expansive, destructive compounds that rip the material apart from the inside. We know the Roman recipe. We have identified the tobermorite crystals under our most powerful microscopes, yet we cannot reliably replicate the exact conditions that cause them to form so perfectly and persistently. Our attempts often create weaker, less stable versions that do not last. The Romans were not just builders, they were geologic alchemists. They created a material that grows stronger with time, that welcomes the very element we fight against. Their concrete was not merely poured, it was born, and it continues to live long after its creators turn to dust. This self-healing property transforms our entire understanding of what a building material can be. Imagine a tiny fissure, a hairline crack, forming in a 2,000-year-old seawall. In modern concrete, this is the beginning of the end. Water seeps in, carrying corrosive salts that attack the internal steel rebar, causing it to rust and expand, which then widens the crack in a vicious, destructive cycle. But in Roman concrete, that same crack is an opportunity. As seawater percolates through the opening, it encounters unreacted pockets of lime and the volcanic ash mixed throughout the material. This triggers a new chemical reaction, forming microscopic, plate-like crystals that grow into the empty space, interlocking to form a perfect mineral seal. The wound does not just get patched, it becomes stronger than the surrounding material. This is not a passive material slowly succumbing to the elements. It is an active system, constantly interacting with its environment to repair itself. Modern material scientists are in a race to catch up to this ancient wisdom. They are experimenting with embedding bacteria or special capsules of healing agents into concrete, trying to mimic this biological-like response. Yet these are complex, expensive additions. The Roman formula achieved this dynamic resilience with just 3 simple, natural ingredients, mixed in a way that turned the sea itself into a maintenance crew. Their concrete was not just built to last, it was designed to live, to adapt, and to endure on a timescale we can scarcely comprehend. This dynamic quality hints at a mindset far removed from our own disposable culture. The Romans were not building for a decade or even a century. They were building for eternity, and the silent, steadfast presence of their harbors is the proof. That same Roman genius for manipulating matter extended far beyond concrete and into the realm of light itself. Deep within the British Museum rests a chalice that seems to defy the very laws of physics. It is the Lycurgus Cup, a stunning Roman artifact from the 4th century. At first glance, it appears to be a beautiful, opaque jade green, but hold it up to a light source and a miracle occurs. The entire cup transforms, glowing from within with a vibrant, translucent ruby red. This is not a trick of the light, it is a property of the glass itself, a phenomenon known as dichroism. For centuries, this magical transformation was a complete mystery. How could the Romans have created a material that changes its very color based on the direction of the light passing through it? The answer, when it was finally uncovered in the 1990s, was more shocking than any legend. Scientists examining slivers of the glass under powerful electron microscopes discovered that the Romans had impregnated the glass with billions of minuscule particles of gold and silver. But these were not mere specks of dust. They were nanoparticles, each one measuring only about 70 nanometers across, smaller than a wavelength of visible light. This was not an accident. The Romans had somehow mastered a form of colloidal chemistry. Suspending these tiny metal particles in the glass melt with perfect precision. The different colors are a result of how these nanoparticles interact with light. In reflected light, the green wavelengths bounce back to our eyes, but when light passes through the cup, the nanoparticles scatter the blue and green light, allowing only the deep red to transmit through, creating that unearthly glow. This precise manipulation of matter at the nanoscale is a cornerstone of modern science, a field we only began to pioneer in the 20th century. The artisans who crafted the Lycurgus Cup had no concept of atoms or nanometers. They possessed no electron microscopes to verify their work. They operated from a place of profound empirical knowledge, a recipe passed down through generations that said, if you add this specific, minuscule amount of gold and silver dust to the glass under these exact conditions, you will capture light itself. The cup is not just a beautiful artifact, it is a silent challenge to our linear view of history, a permanent question mark placed beside our timeline of scientific discovery. How many other secrets of the small did they know that we have yet to relearn? The creation of the Lycurgus Cup was no lucky accident. To achieve that precise color-shifting effect, Roman artisans had to execute a process of breathtaking sophistication, a sequence of steps that required an almost instinctual mastery of their materials. They began by adding a meticulously measured amount of finely ground gold and silver dust to a batch of molten glass, but the real secret lay in what happened next. The cooling of the glass was not left to chance. It was a carefully controlled thermal dance, a slow and specific heating and cooling cycle that allowed the tiny metal fragments to crystallize into nanoparticles of a near-identical size, each one around 70 nanometers in diameter. This precise size was the key to the entire phenomenon, for it dictated exactly how the particles would interact with the different wavelengths of light. This was not a one-off fluke. Multiple examples of Roman dichroic glass have been found, proving this was a repeatable, standardized technique, a technology born from deep empirical observation. They knew that if they followed their unwritten recipe with absolute precision, they could trap light itself within a solid object. The loss of this knowledge represents one of the most profound setbacks in the entire history of science. It effectively erased the field of plasmonics, the study of how light interacts with metal nanostructures, for over 1,000 years. We had to reinvent this entire branch of physics from scratch in the 20th century, only to discover that Roman craftsmen had been practicing its principles all along. They were not just glassmakers, they were unwitting pioneers of the nanoscale, manipulating matter at a level of precision that defies our understanding of their capabilities. This single artifact forces us to ask a deeply unsettling question. What other fundamental truths about our world did they glimpse, only for that vision to be swallowed by the darkness of time? The Romans were not the only ancient civilization to capture light in metal. Half a world away, artisans of China's Han Dynasty perfected an object of equal mystery, the enigmatic black mirror. To the naked eye, it appears unremarkable, a simple disc of polished bronze, dark and smooth. But when you direct a beam of sunlight onto its reflective surface and cast that light onto a wall, an impossibility occurs. The wall does not show a simple circle of light. Instead, it displays a perfect glowing image, a detailed pattern or inscription that exactly matches the intricate design cast onto the mirror's non-reflective back. It is as if the solid bronze has become transparent, allowing the hidden pattern to pass straight through. For centuries, these devices seem to defy the very laws of physics, earning them the name light penetration mirrors. They were not just mirrors, they were the world's first solid-state projectors. The secret, we now know, lies in imperfections so subtle they are almost non-existent. Modern scanning techniques reveal that the surface of the mirror is not perfectly flat. The process of casting the bronze with a thick, decorated back and a thin, reflective front created microscopic internal stresses. When the smiths polished the surface to a brilliant sheen, these stresses caused the thinnest parts of the mirror to bulge outward ever so slightly, creating a curvature variation measured in micrometers. These minuscule high and low points are invisible to the eye and cannot be felt by a fingertip, yet they are precisely aligned with the pattern on the back. When light hits the mirror, the slightly raised areas scatter the light differently than the lower areas. This differential scattering acts like a stencil, projecting the hidden design onto the wall. The effect was likely enhanced by sulfur inclusions from the casting process, which created areas of varying reflectivity within the bronze itself. We can analyze a 2,000-year-old mirror and map its topography with lasers. We can understand the physics of the scattering, but we cannot reliably reproduce the exact multi-step casting, cooling, and polishing technique that consistently creates this precise, invisible warping. The Han artisans were masters of stress metallurgy, controlling forces within the bronze to achieve an optical miracle. They were not just polishing metal, they were encoding an image into its very structure, a secret message written in stress and light, waiting for the sun to read it aloud. The black mirror's magic is etched into its stressed crystalline lattice. To understand how, we must peer into the moment of its creation, when the glowing bronze disc was pulled from the furnace. The artisan did not let it cool slowly. Instead, they plunged it, hissing and steaming, into a quenching bath. This violent thermal shock is the heart of the phenomenon. The thicker, decorated back of the mirror cools and contracts at a much slower rate than the thin, delicate front. This imbalance locks powerful internal stresses into the metal, an invisible battlefield of competing forces. The result is a surface that looks perfectly smooth but is, in fact, microscopically warped. These warps are not random. They are a perfect, invisible map of the design on the back, with the raised lines of the pattern causing corresponding high points on the reflective front. When sunlight strikes this stressed surface, it does not simply bounce off. The microscopic high and low points act as a natural diffraction, grating, bending, and scattering the light. The areas aligned with the thick parts of the pattern scatter the light away, while the rest reflects it directly. This creates a stark contrast on the wall, projecting the hidden image as if by sorcery. A modern engineer, with their precise temperature controls and laser scanners, could measure these warps. They could even design a machine to etch a similar pattern onto a mirror's surface. But that would miss the entire point. The Han Dynasty artisan did not need a machine. They possessed an intuitive, tactile understanding of the quenching process. They knew the exact color of the hot bronze, the precise moment to quench it, and the specific composition of the cooling liquid to achieve that perfect internal stress map. This was knowledge written in muscle memory and passed down through generations, a perfect symphony of art, physics, and metallurgy. Our modern precision engineering can analyze the effect, but it cannot replicate the ancient human genius that first conceived it. The mirror's secret remains locked not in its formula, but in the long-lost rhythm of the artisan's hands. Far from the sophisticated workshops of Rome and China, in the smoky forges of the Viking Age, another metal mystery was being hammered into existence. It was a weapon so superior that its name was inscribed right into the blade for all to see and fear. Plus ULFBERHT plus T. The Ulfberht sword was the superweapon of its day, a gleaming length of steel that would not break when other blades shattered, that held a sharper edge, and that flexed and returned true when a rival's weapon would have bent. For a Viking warrior, possessing an Ulfberht was like wielding a sliver of the future on a battlefield stuck in the past. The secret was in the steel itself. While most European swords of the era were made from inferior, slag-filled iron that was brittle and unreliable, the Ulfberht was forged from a material called Crucible steel. This was a high-carbon steel of astounding purity. Its carbon content was nearly 3 times that of its contemporaries, and it contained almost none of the damaging impurities that weakened other blades. This purity gave the Ulfberht its legendary combination of hardness and flexibility, a paradox that medieval smiths could not solve. But where did this miraculous steel come from? The Vikings did not possess the technology to create it themselves. The answer lies not in a Scandinavian forge, but along the vast intercontinental trade routes of the medieval world. The raw material for Ulfberht blades almost certainly originated thousands of miles to the east, in the Crucible steel production centers of Central Asia, likely in modern-day Iran or Afghanistan. This was a product of globalization, a material that traveled along the Volga trade routes, passing through the hands of merchants and traders before finally reaching the master smiths, probably in the Frankish Empire, who worked the steel and stamped it with that famous name. The Ulfberht was not just a local innovation. It was a global citizen born from the meeting of Eastern material science and Western martial need. Its existence depended on a fragile, open pipeline of knowledge and resources that stretched across the known world. Then that pipeline was severed. Political upheavals, the collapse of trade networks, and the Mongol invasions likely cut off the supply of that high-quality Crucible steel from the east. The knowledge of how to work it was lost with the last generation of smiths who understood its properties. But the most baffling aspect of the Ulfberht is the furnace required to make it. To create Crucible steel, you must completely liquefy the iron and carbon mixture, allowing impurities to separate and the carbon to dissolve evenly. This requires a sustained, intense heat that medieval European furnaces simply could not achieve. The technology needed to reach that melting point, around 3,000 degrees Fahrenheit, would not reappear in Europe until the Industrial Revolution, nearly 8 centuries later. So how did they do it? We do not know. Perhaps they used a specific, powerful furnace design fueled by a particular type of charcoal, creating a draft hot enough to achieve the impossible. The Ulfberht stands as a stark reminder that technological progress is not a steady climb. It is a flickering flame, one that can be lit, can burn brightly for a time, and can then be snuffed out, leaving only a ghost of its warmth and a mystery written in steel. That crucible was a tiny, sealed universe where iron was reborn. Inside the thick clay pot, raw iron was packed tightly together with pieces of charcoal or other organic material rich in carbon. The lid was sealed shut, creating a miniature, controlled environment that was then placed into the heart of a furnace. For hours, the fire raged around it, not merely heating the contents but transforming them. The temperature inside had to climb to a staggering 1,500 degrees Celsius, a white-hot fury that was far beyond the capability of ordinary forges. At this extreme heat, the solid iron did not just soften, it actually melted, becoming a seething, liquid pool. This liquefaction was the key to everything. In a standard bloomery furnace, iron never fully melted, leaving it riddled with pockets of silica and other rocky impurities called slag. But inside the sealed crucible, these impurities, being lighter, simply floated to the top of the molten metal, where they could be skimmed off or left behind when the ingot was poured. Meanwhile, the liquid iron greedily absorbed the carbon from the charcoal, creating a perfectly homogeneous, high-carbon steel alloy. When the crucible was finally cracked open after a slow, controlled cooling, what emerged was not a lump of crude iron, but a gleaming ingot of pure crucible steel, its internal structure uniform and free of the weaknesses that plagued other metals of the age. This was the raw material of legend, the heart of the Ulfberht. The technological sophistication required to achieve this is difficult to overstate. It was not just about building a hot fire, it was about engineering a thermal environment that could sustain that incredible heat for a prolonged period. The furnace design, the type of charcoal used, and the skill of the fire tender who managed the draft were all critical, unwritten parts of the recipe. This was not a simple blacksmith's forge, it was a precision chemical reactor built from clay and flame. The fact that this knowledge emerged in Europe, only to vanish completely after the Viking Age, is one of history's great paradoxes. It represents a clear, demonstrable regression in human capability. For centuries, European metallurgy slid backwards, unable to replicate the purity of steel that a handful of master smiths had once produced as a matter of course. We can, of course, create steel of equal or greater quality today using modern electric arc furnaces and controlled atmospheres, but that is the entire point of the mystery. Our mastery is built on a completely different, industrialized foundation. The historical method, the specific combination of clay, heat, and human skill that consistently produced those legendary ingots, remains just out of reach. The Viking forge was a flickering beacon of advanced materials science in an age we mistakenly called dark, and its light went out for reasons we still do not fully understand. That paradox of the Viking forge, a brief flare of advanced science in the so-called Dark Ages, finds a stunning parallel far across the Atlantic Ocean. In the workshops of ancient South America, centuries before European contact, artisans were creating objects from one of the most stubborn metals on Earth, platinum. This presented a seemingly impossible barrier. Platinum does not even begin to melt until it reaches a scorching 1,768 degrees Celsius, a temperature far beyond the reach of any pre-Columbian furnace. It was a metal they could mine and hold, but could never hope to pour or cast by conventional means, so they devised a workaround of pure genius, a method that sidestepped the problem of heat entirely. Instead of trying to melt the platinum, they broke it down. They would take the native platinum grains found in riverbeds and painstakingly hammer them into an even finer powder. To this, they added a crucial ingredient, gold dust. The mixture of platinum powder and gold was then placed in a crucible and heated. While the temperature was still far below platinum's melting point, it was more than enough to melt the gold. The liquid gold would flow around the individual solid particles of platinum, acting as a natural solder, bonding them together into a solid mass. This process, known as sintering, created a durable, beautiful alloy of white gold and platinum, used for nose rings, masks, and other ceremonial objects. They were not smelting the metal, they were fusing it, building a solid object grain by grain. This was a form of powder metallurgy, a technique that European industry would not formally develop until the 19th century. The solution was not to build a hotter fire, but to think in an entirely different way about what it means to shape a metal. They looked at a problem defined by extreme heat and found an elegant, low-temperature answer. This was more than just clever craft. It was a different philosophy of making, one that proves innovation is not always about overcoming a barrier with brute force, but about finding a smarter path around it. This sintering process was a meticulous act of assembly. Artisans along the Pacific coast of what is now Ecuador and Colombia would gather small, naturally occurring nuggets of platinum from river sands. These dense, gray grains were far too refractory to melt, so they were carefully hammered into an even finer powder. This platinum dust was then mixed with precise amounts of gold and sometimes copper dust in a clay-lined ceramic vessel. When heated in a furnace, the magic began. The gold, with its much lower melting point, would liquefy long before the platinum even thought of softening. This molten gold acted as a perfect natural glue, flowing into every crevice between the stubborn platinum particles, wetting their surfaces and locking them into a cohesive, solid mass as it cooled. The result was not a true melt, but a composite material, a durable, corrosion-resistant alloy that gleamed with a distinctive, pale luster. This technique is the very foundation of modern powder metallurgy, used today to create everything from complex gear parts to porous medical implants. Yet these ancient American smiths developed it entirely on their own, without any contact with the old world. They saw a problem that seemed insurmountable and devised a brilliantly elegant solution, building a metal object not from a liquid pore but from a solid-state fusion. This unique metallurgical pathway, however, was abruptly closed by the arrival of Europeans. The conquest and the cultural collapse that followed severed the chain of knowledge. The specific recipes, the nuanced understanding of temperatures and mixtures, and the very reason for seeking out that strange, heavy river metal were lost. For centuries, this sophisticated technique vanished from the region, a silent testament to a way of thinking about materials that was snuffed out before it could spread any further. That same philosophy of building materials from the inside out finds its most monumental expression not in a weapon or a tool, but in a silent 7-ton sentinel. The iron pillar of Delhi has stood in a humid, tropical environment for over 1,600 years, completely exposed to the elements. If it were made of modern wrought iron, it would have oxidized into a pile of red dust centuries ago. Yet it remains almost entirely free of rust, its surface bearing only a thin, dark gray protective film. This is not a story of a lost alloy, but of a lost protective process, a form of ancient self-preservation we are still struggling to engineer on a large scale. The secret is not in the iron itself, but in a microscopic shield that guards it. Scientists discovered that the pillar is coated in a thin, complex layer called mesowite. This is not ordinary rust. It is a special film of iron, oxygen, hydrogen, and a crucial third element, phosphorus. This mesowite layer is what we call a passive layer. It is incredibly stable and non-porous, forming a perfect barrier that prevents oxygen and moisture from reaching the pure metal beneath. It is the pillar's own personal, ever-present suit of armor. The high phosphorus content is the key, but it was not an intentional additive. It was a happy accident of an ancient process. The iron ore used by the Gupta dynasty smiths was naturally rich in phosphorus. Their unique, low-temperature smelting method in small clay furnaces failed to remove this phosphorus, which was typically considered an impurity that makes modern steel brittle. In this specific case, however, that impurity became the pillar's salvation. Over the first few years of its life, the phosphorus in the iron slowly reacted with the air and rain, catalyzing the formation of that protective mesowite film. Once the film was established, it became a permanent guardian. We can analyze this film down to the atomic level. We know its chemical composition. The challenge is one of scale and control. Modern steel production efficiently removes phosphorus to prevent brittleness. To replicate the pillar's protection, we would have to deliberately reintroduce high levels of phosphorus in a specific way, under specific conditions, across an entire massive structure. We have not yet mastered how to do this consistently and reliably for something like a modern bridge or a ship's hull. The pillar, therefore, is more than a marvel. It is a challenge. It proves that long-term durability is not always about creating a perfectly pure material. but sometimes about fostering the right kind of imperfection. It stands as a permanent lesson in passive protection, a quiet giant reminding us that the most resilient defense is often a shield that grows from within. This protective film is not just a simple barrier. It works by fundamentally disrupting the chemistry of corrosion at the atomic level. The high concentration of phosphorus atoms scattered throughout the iron acts as a permanent defense. They occupy the very sites on the metal surface where the destructive reaction of rust would normally begin and then accelerate. It is as if the phosphorus places a permanent lock on the doors that rust needs to open, preventing the corrosive chain reaction from ever gaining a foothold. This initial forging process was crucial. As the massive pillar cooled from its creation, its surface began a slow, deliberate conversation with the atmosphere. The phosphorus, present as an unplanned guest in the iron, reacted with oxygen and moisture to build that initial, thin layer of mesowite. Once established, this film is not static. Minor scratches or abrasions that expose fresh iron are quickly addressed. The surrounding phosphorus reacts again, forming new protective compounds that heal the breach, making the shield self-repairing over time. This is where the ancient method diverges so profoundly from our own. Modern metallurgy is a quest for purity. We process iron ore to meticulously strip away phosphorus because we know it makes steel brittle and prone to cracking in cold weather, a critical flaw for things like bridges and ship hulls. The ancient smiths were not trying to achieve a universal material. They were solving a specific problem with the tools they had. Their available iron ore was rich in phosphorus, and instead of seeing it as a flaw to be eliminated, they discovered how to harness its unique defensive properties for a monumental, stationary object in a warm climate. They embraced the so-called impurity and turned it into the pillar's greatest strength. This represents a completely different philosophy of making. It is the wisdom of working in harmony with the natural character of a material, rather than forcing it to conform to an abstract ideal. The pillar's longevity is a testament to this adaptive genius, a permanent monument to the power of an intelligent imperfection. The wisdom of embracing imperfection finds its ultimate expression in a metal that may never have existed at all. Plato, the great philosopher of ancient Greece, wrote of a magnificent island empire called Atlantis, a civilization of unparalleled power and wealth. Among its many wonders, he described a mysterious metal called Orichalcum, a substance he claimed was second only to gold in value, shining with a fiery red light and used to sheath the inner walls of the city's central temple. For centuries, this was dismissed as pure myth, a fictional element in a cautionary tale. Then, a shipwreck changed everything. Off the coast of Sicily, divers discovered the remains of a vessel that sank around 2,600 years ago, a time when Plato's story was already an ancient memory. Among the wreckage lay a cargo of strange metal ingots, their composition unlike anything typically traded. Laboratory analysis revealed they were made of brass, an alloy of copper and zinc, but with a unique signature that included small, precise amounts of nickel, lead, and iron. This was not the simple brass of everyday objects. This was a deliberately engineered material, a special alloy that some archaeologists now boldly suggest could be the legendary Orichalcum. The discovery is tantalizing, but it raises more questions than it answers. If these ingots are indeed Orichalcum, then the myth has a physical form. Yet, what made it so precious? We know its basic recipe, but we do not know the magic in its making. Was it the specific ratio of metals that gave it a legendary golden red luster unmatched by ordinary brass? Was it a unique property, like a remarkable resistance to tarnishing, that made it gleam for generations? Or was its value tied to a lost manufacturing process that imbued it with a symbolic or even a perceived mystical quality? The ingots from the sea are a ghost of a ghost. They prove that someone, somewhere, was producing a sophisticated and rare brass alloy that matched the general description of Plato's metal. But they cannot tell us if this was the actual Orichalcum of Atlantis, or simply one culture's attempt to replicate a legend that was already old in their own time. The search for Orichalcum is therefore a double quest. It is an archaeological hunt for physical evidence and a metaphysical journey into the power of a story. It is the search for a myth-made metal, and a reminder that the value of a material is sometimes written not just in its atoms, but in the dreams it inspires. But what did those strange ingots from the sea actually contain? X-ray fluorescence scans revealed a precise alloy of 75 to 80% copper, 15 to 20% zinc, and a cocktail of trace elements including nickel, lead, and iron. This confirmed it was a sophisticated, man-made brass, but the chemical breakdown alone cannot account for a legend. A modern lab can easily reproduce this formula, yet the result feels ordinary, lacking the fiery red glow Plato described. This gap between the chemical facts and the mythical reputation points to a deeper truth. The value of Orichalcum almost certainly lay beyond the periodic table. Perhaps the secret was in the finishing. A specific, laborious polishing technique using rare abrasives could have given its surface a unique, deep luster, a visual warmth that set it apart from common gold or bronze. Or maybe its worth was acoustic. In a world without electronic amplification, the sound a metal made was profoundly important. This particular alloy, with its specific trace elements, might have produced a bell-like tone of unparalleled clarity and resonance when struck, making it the perfect material for ceremonial gongs or sacred instruments. Its value would then have been both visual and auditory, a feast for the eyes and the soul. Another possibility lies in its origin. The zinc used in the alloy likely came from smelting a specific calamine ore. That single ore deposit, now lost to time, could have contained unique impurities, minute amounts of manganese or arsenic, that subtly altered the metal's color or its resistance to tarnishing, giving it a permanent, rosy hue that no other brass could match. The ingots are a vital clue, a physical key, but the lock it opens leads to a room we cannot fully enter. We can hold a piece of the metal, but we cannot hear the song it sang in a temple we have never seen. Orichalcum's true composition was a blend of chemistry, craftsmanship, and ceremony, a formula where the most crucial ingredient was its story. This is the ultimate lesson of the lost metals. Their worth was never just in their atoms, but in the human hands that shaped them and the cultures that cherished them. That universal quest for the perfect blade echoes not only in history, but in our deepest legends. Across medieval Europe, tales were told of swords forged not in any mortal fire. There was Durandal, the unbreakable blade of the knight Roland, said to be indestructible and imbued with holy relics. And of course, there was the sword in the stone, a weapon that could only be wielded by the one true king, its metal gleaming with an otherworldly promise. These are stories, yes, but they share a curious and specific language with the very real mysteries we have explored. They speak of edges that never dull, of surfaces that never rust, and of a strength that defies any earthly force. This is more than simple poetic exaggeration. It sounds remarkably like a folk memory, a distorted echo of a time when such superior weapons did indeed walk the earth. When a community had only known soft iron blades that bent and shattered in battle, the appearance of a single, resilient sword of pure crucible steel would have seemed nothing short of miraculous. Its owner would be seen as chosen, its origin as divine. The legend of the sword in the stone is a powerful metaphor for a leader proving their worth, but it may also be a distant cultural memory of a very real technological test. Perhaps the stone was not literal rock, but a metaphor for a specific, incredibly hard material used to test a blade's quality. A sword that could cleave such a substance without damage would indeed be a kingly weapon. The blacksmith who could create such a blade would be seen as a master of mystical arts, his forge a place of alchemy. This connection between legendary perfection and lost reality reveals something fundamental about our relationship with technology. We are drawn to these stories of unbreakable swords because they represent an ideal, the ultimate achievement of craft that has been severed from our present. They are the ghost in our collective machine, a persistent whisper that we once knew how to make things that lasted forever. The quest for Excalibur is, in its heart, the same quest that drives a modern metallurgist staring at an electron micrograph of Damascus steel. It is the human yearning to recover a paradise of permanence, a world where our finest tools are as enduring as our greatest stories. The legend of Excalibur is more than a fairy tale, it is a cultural fossil. When a society loses the capability to produce a technology that once defined its power, it does not simply forget. It transforms the memory into myth, attributing the creation of such wonders to gods, wizards, or chosen heroes. This process explains why so many legendary swords share a specific, almost technical set of qualities, an unbreakable strength and an undulling edge that sound less like magic and more like the properties of a lost material science. A chieftain in post-Roman Britain, wielding a sword of superior crucible steel imported from a dying trade route, would have possessed an undeniable advantage. His weapon would not bend in the heat of battle, it would cut through the inferior iron of his enemies, and its gleaming, patterned surface would have seemed otherworldly. To the warriors who saw it, this was not advanced metallurgy, it was a divine blessing. The story of the sword in the stone is a perfect metaphor for this. The magical test to prove a king might be a folk memory of a very real physical test of a blade's quality. Perhaps the stone was not literal rock, but a specific, incredibly hard anvil material or a block of particularly tough wood. A sword that could strike this substance without chipping or breaking would be a weapon worthy of a legend, and the smith who forged it would be remembered as a sorcerer. By carefully separating the magical narrative from the physical descriptions in these stories, historians and scientists can find a trail of breadcrumbs. The insistence on a sword that never rusts points directly to the mystery of passive layers like that on the iron pillar. The description of a blade that can cut through stone and iron alike echoes the legendary sharpness of Damascus steel. These myths are not random inventions, they are the echo of a real, ringing blow struck by a metal that we can no longer make. They are the ghost of a technological peak, a story that outlived the very knowledge that inspired it. The legend of unbreakable swords finds a strange parallel in the story of a Roman emperor and a bowl that refused to shatter. Ancient historians recorded a curious tale of an artisan who invented a new kind of glass. He fashioned a drinking bowl from this material and, in a dramatic audience with Emperor Tiberius, demonstrated its unique property. He threw the vessel onto the stone floor. Instead of fracturing into 1,000 pieces, it merely dented. With a few taps from a small hammer, he popped the dent out, restoring the bowl to its original, perfect shape. This was vitrum flexile, flexible glass. The emperor was first amazed, then deeply troubled. He asked the inventor if anyone else knew the secret of this miraculous material. When the man swore he was the only one, Tiberius had him beheaded on the spot and his workshop utterly demolished. The emperor's logic was brutally economic. He feared that a substance as beautiful as silver or gold, yet seemingly indestructible, would completely destabilize the value of precious metals and ruin the empire's treasury. This story, likely more fable than fact, reveals a profound anxiety about disruptive technology. It is one of the earliest recorded instances of innovation being suppressed not for safety or morality, but purely to protect an established economic order. The artisan was not killed for failing, but for succeeding too well. Today, we chase the same dream with tempered glass and advanced polymers. We have Gorilla Glass on our phones, which is remarkably resistant to scratches and cracks, but it is not truly flexible in the way the Roman legend describes. Creating a transparent solid that can be bent and dented like metal at room temperature without losing its clarity or strength remains a holy grail of materials science. The story of Vitrum Flexile is a ghost of a road not taken. It makes us wonder how many other breakthroughs were lost not to the natural decay of time, but to the deliberate, decisive swing of an axe. That emperor's brutal decision may have cost us a material that could have reshaped the world. The ancient dream of Vitrum Flexile is not just a myth, it is the very frontier of modern materials science. We understand exactly why ordinary glass is so fragile. Its atoms are arranged in a chaotic, amorphous network, lacking the orderly, sliding planes found in crystalline metals. When stress is applied, this disordered structure cannot distribute the force, so instead of bending, it develops a tiny crack that instantly propagates, leading to a catastrophic shatter. This is the nature of brittleness. Yet, in laboratories today, scientists are chasing the ghost of that Roman legend by creating a new class of materials known as bulk metallic glasses. These are metals cooled so rapidly from their liquid state that their atoms do not have time to form a rigid crystal lattice. They freeze in a glass-like, disordered structure. The result is a material that can be as strong as steel, but with a remarkable property. Under stress, it does not crack immediately. Instead, it deforms plastically, bending and denting before finally failing, much like the emperor's mythical bowl. But there is a profound catch. These metallic glasses are opaque. They possess the toughness of the legend, but they lack its defining feature, transparency. The ultimate goal, the true Holy Grail, is a material that is both transparent and ductile, one that combines the clarity of glass with the forgiving resilience of metal. Researchers are experimenting with exotic compositions, from complex zirconium alloys to new forms of organic glass, trying to trick atoms into forming a structure that can both let light pass and allow for plastic flow. The ancient story of Vitrum Flexile, whether it was real or not, represents a path that was lost, the potential discovery, snuffed out by a single act of suppression, arguably set back the entire field of materials science by well over 1,000 years. We are only now, with our electron microscopes and molecular modeling, beginning to approach a dream that one artisan might have held in his hands. The quest for unbreakable glass is a 2,000-year-old race, and we are still trying to catch up to a ghost. That emperor's fear of disruptive technology reveals a pattern of loss, but sometimes the most profound disappearance is not of a single material, but of an entire system of thought. Resting silently at the bottom of the Mediterranean Sea for 2 millennia lay a corroded lump of bronze and wood that would shatter our understanding of ancient science. When sponge divers first pulled it from a Roman shipwreck near the island of Antikythera in 1901, they had no idea they were holding the most technologically complex object from the ancient world. It was the Antikythera mechanism, an intricate astronomical computer built from dozens of interlocking bronze gears. This was not a simple calendar. It was a portable cosmos of precision engineering, a device that could predict planetary positions, lunar phases, and even the timing of Olympic Games with stunning accuracy. Its very existence is a historical shock, a technological island in a sea of time. The sophistication of its geared calculations would not be matched again until the great astronomical clocks of 14th century Europe. For over 1,000 years, the knowledge required to build such a device simply vanished from human history. The genius of the mechanism was not merely in its mathematical theory, but in the physical material that made it possible, the special bronze from which its gears were forged. This was no ordinary metal. The gears had to be incredibly precise, with teeth cut finer than a modern watch. They had to mesh together with minimal friction, turning smoothly for decades without seizing up. And they had to resist the corrosive wear that would destroy their delicate calibrations. The alloy used was a specific type of bronze, cast and worked to achieve properties we still struggle to replicate with complete fidelity using ancient methods. Modern analysis shows it was a low tin bronze, likely around 5 to 7% tin, mixed with a small, deliberate amount of lead. This specific recipe created a metal that was hard enough to maintain its shape under stress, yet soft enough to be machined with incredible precision using hand tools. The lead acted as an internal lubricant, reducing friction between the meshing gears. But knowing the chemical formula is like having a list of ingredients without the cooking instructions. How did ancient artisans achieve such flawless consistency in their alloy? How did they cast such thin, complex gear blanks without introducing bubbles or imperfections that would cause a gear to crack under strain? And with only files, drills, and hand-powered lathes, how did they cut those minuscule teeth with such geometric perfection that the entire assembly functioned as a harmonious mechanical whole? The metal itself was the canvas, but the lost art was the painting. The Antikythera mechanism forces a humbling realization. We often picture the ancient world as a place of philosophy and simple mechanics, of levers and pulleys. This device tells a different story. It speaks of a hidden lineage of engineers, of workshops where artisans understood material properties and precision, manufacturing on a level that borders on the magical. The bronze gears are not just cogs in a machine, they are the physical echoes of a lost intellectual universe, a world where the boundaries between art, science, and craft were seamlessly woven into a single, breathtaking creation. The silicon of its age was not just mixed, it was born in fire and wax. To create a gear for the Antikythera mechanism, an artisan began not with metal, but with a painstakingly carved model of the gear in beeswax, complete with its minuscule, precisely spaced teeth. This wax model was then encased in a clay mold, and the entire assembly was fired. The wax would melt and drain away, leaving behind a perfect, hollow negative space in the hardened clay, a cavity waiting for liquid bronze. This lost wax process was known across the ancient world, but the level of precision achieved here was extraordinary. The slightest imperfection in the wax carving, a single tooth cut a fraction too wide, would render the entire gear useless. The mold had to be heated to the exact same temperature as the molten bronze to prevent thermal shock, which could cause tiny cracks or distortions, and then there was the pour itself. The bronze, a specific alloy of copper and tin, had to be fluid enough to fill every microscopic crevice of the mold, yet cool without forming bubbles or pockets of air called porosity. Any porosity inside a gear tooth would create a weak point, a hidden fault line that would inevitably fail under the constant stress of meshing and turning. The artisans who made these gears possessed a deep, intuitive understanding of their material. They knew that a higher tin content made the bronze harder and more durable, but also more brittle and difficult to cast with fine detail. A lower tin content made the metal more fluid for casting but too soft, and the gear teeth would wear down quickly. They had found a perfect, golden ratio, a recipe that balanced castability with long-term mechanical integrity. This was not a single discovery, but a cumulative body of knowledge passed from master to apprentice, a living library of metallurgical nuance. We can analyze the bronze and know its composition. We can even create perfect replicas using computer-controlled milling machines and modern foundries. But this misses the profound mystery. The original creators had none of these tools. Their precision was achieved with the naked eye, a steady hand, and a lifetime of accumulated skill. The loss of this specific, hands-on knowledge for precision casting is a chasm in the history of engineering. It represents the disappearance of an entire school of thought dedicated to miniaturization and durability, a technological path that was abandoned and forgotten, leaving behind only a corroded, miraculous ghost in a shipwreck. That same spirit of holistic creation, where the artisan's intuition guides the very atoms of the metal, finds one of its purest expressions not in Rome or Damascus, but in the mountains of feudal Japan. Here, the quest for the perfect blade began not with an ingot, but with the earth itself. The raw material was not iron ore, but a unique black sand, rich in iron, collected from riverbeds and coastlines. This sand was placed inside a massive clay box furnace called a Tatara, a temporary structure that was painstakingly built and then destroyed after a single epic smelt. For 3 days and 3 nights, the master smelter and his team would feed this furnace with alternating layers of iron sand and vast quantities of charcoal. This was not a process controlled by thermometers or digital readouts. The master read the fire's color, its sound, even the taste of the air, making constant, intuitive adjustments to the airflow and fuel. He was not just heating metal, he was cultivating it. The result of this grueling, almost ritualistic process was a heterogeneous block of steel called tamahagane. This was not a uniform slab. It was a chaotic, beautiful mess of steel with wildly varying carbon content. Some parts were high carbon, hard and brittle. Others were low carbon, soft and flexible. To any modern factory, this inconsistency would be a failure, but to the Japanese swordsmith, it was the raw material of genius. He would take this block and break it apart, carefully sorting the pieces by their carbon content and color, reading the metal like a language only he could understand. The true magic began in the forge. The smith would then take these sorted pieces and weld them together, stacking the hard, high-carbon steel to form the razor-sharp edge of the blade, and the softer, more resilient low-carbon steel to form its core and back. He would then fold and hammer this composite block, not just a few times, but over and over, sometimes more than a dozen times. This created thousands of microscopic layers, an intricate laminar structure that was both a work of art and a feat of engineering. The final blade was a paradox made solid. The hard steel edge could be sharpened to a molecular fineness, capable of making the most precise cuts. The softer, flexible spine absorbed the shock of impact, preventing the blade from snapping. This combination is the very soul of the katana, a balance that a single piece of uniform, modern monosteel struggles to achieve. We can make steel harder, or we can make it tougher, but replicating that perfect internal harmony of properties within a single blade remains the ultimate challenge. The process was never just about metallurgy. It was a spiritual journey, a discipline where the smith's own focus and resolve were believed to be hammered into the steel itself. The katana was not merely manufactured, it was born, and each one carries the unique signature of its creator, a fingerprint in folded steel that we can admire but never truly duplicate. The Tatara furnace is a living, breathing entity, a temporary temple of fire built from earth and clay. For 3 days and 3 nights, the Murage, the master smelter, does not sleep. He becomes an extension of the furnace itself, his senses tuned to its every whisper. He reads the subtle shifts in the flame's color, from a deep orange to a piercing yellow-white. He listens to the roar of the air being drawn through the clay walls, a sound that tells him if the combustion is perfect. He even tastes the air, detecting the faint, metallic tang of vaporizing impurities. This is not a process that can be run by a computer. Every adjustment, every decision to add more charcoal or iron sand is an act of profound intuition, a dialogue between human and element. The goal is not a uniform industrial product. It is the creation of Tamahagane, the jewel steel. When the furnace is finally broken open, what emerges is a rough, spongy mass, a chaotic tapestry of steel with carbon content varying wildly from one spot to the next. To a modern engineer, this inconsistency would be a catastrophic failure, but to the swordsmith, it is a palette of possibilities. He carefully breaks apart the mass, sorting the pieces by their color and texture. The brighter, harder high-carbon steel will become the sword's lethal edge. The darker, softer low-carbon steel will form its resilient, shock-absorbing core. This laborious sorting is the first step in a process where the smith does not fight the metal's natural variations, but instead collaborates with them. He is not imposing a single, uniform property, but weaving a complex internal harmony. This is the antithesis of mass production. A factory line demands consistency and speed, erasing all individuality from its products. The katana, born from the Tatara, is inherently unique. Its very soul is forged from this intimate, almost spiritual partnership between the murage who coaxes the steel from the earth and the smith who coaxes the sword from the steel. The knowledge may be preserved in books, but the deep, intuitive mastery, the spirit required to read the fire and understand the metal's soul, is a fading light. In a world of perfect, identical objects, the katana stands as a testament to the beauty of intelligent imperfection. A blade that is as much a reflection of its creator's spirit as it is a weapon. From the folded steel of the katana, we turn to a king who sought to forge an even more personal kind of armor, one not of metal, but of his own blood. The legend of Mithridates VI of Pontus is a story of paranoia turned into a lifelong experiment. Fearing assassination by poison, this ancient ruler dedicated himself to creating a universal antidote, a potion that would make him invulnerable to any toxic substance. He called his concoction Mithridatium. The recipe was his most closely guarded secret, a complex blend of dozens of ingredients that historians believe included various metal compounds and oxides. Imagine a medicine cabinet filled not with herbs, but with powdered gold, mercury, arsenic, and other metallic substances we now know to be deadly. This was the world of ancient metallopharmaceuticals, where the line between poison and cure was dangerously thin. Mithridates was practicing a form of alchemy, but his goal was not to create gold. It was to transform his own body into a fortress, using metals as the building blocks of his immunity. He reportedly took small, daily doses of his potion, building up a tolerance in a process we now call Mithridatism. The legends say he became so immune that when he was finally captured by the Romans and attempted suicide, even poison would not work. He had to order a soldier to run him through with a sword. The recipe for his legendary antidote died with him, a secret he took to his grave. What were those precise metallic ingredients, and in what miraculous balance did they somehow counteract toxins instead of causing them? We can only guess, because that entire branch of experimental, metal-based medicine has been largely lost to history. This was not mere superstition. It was a lost branch of proto-chemistry, a bold and dangerous exploration of how inorganic matter interacts with the complex chemistry of the human body. They were, in their own way, pioneering the concept of using one substance to counter the effects of another at a biological level. While we now understand the terrible toxicity of lead or mercury, the underlying principle of Mithridatium has a startling echo in our most advanced modern medicine. Today's immunotherapy for cancer or autoimmune diseases works on a similar foundational idea, carefully calibrating complex compounds to train the body's own defenses, to turn a biological weakness into a strength. The ancient alchemists were groping in the dark with tools we now know to be perilous, but their goal, to harness chemistry for bodily resilience, was centuries ahead of its time. The loss of Mithridatium is not the loss of a safe medicine, but the loss of an entire philosophical approach to healing, a road not taken in our scientific history. Mithridates was not alone in his belief that metals held a cosmic key to health. This idea was the very heart of alchemy, a philosophy where chemistry and spirituality were indivisible. Alchemists saw the universe as a grand, interconnected system, and they believed that the pure, untarnishable nature of gold reflected a state of perfect balance and immortality. By consuming gold or medicines derived from it, they hoped to transfer that perfection and stability into the human body, conferring longevity and even eternal life. Silver, with its cool, lunar sheen, was linked to the mind and purity. Iron, the metal of Mars, was associated with strength and vitality. Each metal was not just a substance, it was a reservoir of celestial energy. Their methods were a form of applied material science, albeit guided by a spiritual map. They would transform metals through processes like oxidation, creating rusts and other compounds, or dissolve them in powerful acids to create tinctures. They were manipulating matter at a fundamental level, trying to unlock its hidden virtues. While their underlying theory about cosmic energies was incorrect, their hands-on work was a rigorous, if dangerous, form of empirical experimentation. They were meticulous record keepers, documenting the precise effects of mercury, arsenic, and lead compounds on the human body. They noted which preparations caused paralysis, which induced vivid dreams, and which, in minuscule, carefully calibrated doses, seemed to alleviate certain symptoms. This accumulated data represented centuries of observational research into metallotherapeutics. The tragic loss of these alchemical libraries, often dismissed as mere superstition, was a catastrophic erasure of raw data. We did not just lose a few fantastical recipes for elixirs of life. We lost a massive, long-term, and brutally honest catalogue of how metal compounds interact with human biology. Their quest for a panacea was misguided, but it was driven by a profound desire to use the power of materials to conquer human suffering. In their own flawed way, they were the first toxicologists and the first pharmacologists, pioneers who walked a perilous path and left behind maps we can no longer read. That alchemical dream of transmuting one metal into another found a stunningly practical reality in the ancient art of brass making. Long before anyone understood the chemistry of zinc, metal workers had perfected a remarkable process to infuse common copper with a golden hue and superior properties. They could not simply melt zinc and mix it in because zinc metal boils away into a vapor long before copper even begins to melt. So they devised a brilliant workaround, a method known as cementation. Inside a sealed clay crucible, an artisan would carefully layer pieces of copper metal with charcoal and a zinc-bearing ore, most often smithsonite. The crucible was then sealed shut and heated for many hours. As the temperature rose, the zinc inside the ore would not melt. Instead, it would instantly transform into a vapor, a zinc gas that filled the tiny enclosed space. This invisible cloud of metal would then diffuse directly into the solid copper, atom by atom, transforming its very nature from the inside out. The result was not a simple coating, but a true alloy, a homogeneous brass. The skill required to control this gaseous alchemy was immense. The temperature had to be high enough to vaporize the zinc, but not so high that the copper itself began to melt or that the vapor pressure blew the lid off the crucible. The heating time had to be just right, too short, and only the surface of the copper would turn to brass, leaving a soft copper core. Too long, and the zinc could begin to leak out, leaving the metal brittle. The master artisan had no gauges. He judged the process by the color of the fire and the faint hissing sounds from the crucible, making subtle adjustments based on a deep, tactile knowledge. We can describe this process perfectly today. We know it was a form of gas phase alloying, a sophisticated technique where a solid metal absorbs a vapor. But knowing the theory is not the same as possessing the art. Modern industry smelts zinc metal directly in sealed retorts, giving us perfect control over the composition of our brass. Yet, when we analyze some ancient brass artifacts, we find a subtlety and a consistency that our brute force methods struggle to mimic. The loss is not of the recipe, but of the nuanced sensory skill that allowed an ancient metalworker to conduct an invisible orchestra of heat and vapor, turning stone and copper into golden brass through a secret dance of atoms in a sealed clay pot. These volatile metals were like ghosts in the ancient workshop, substances that threatened to vanish into thin air with the slightest misstep. Zinc was particularly elusive, boiling away into an invisible, metallic vapor long before it could ever pool into a liquid metal. To capture it, artisans had to think like trapdoor spiders, creating a sealed environment where the metal could not escape. The cementation crucible was that trap. Packed with copper, charcoal, and zinc ore, then sealed shut, the crucible became a miniature chemical reactor. Inside, the intense heat transformed the solid zinc ore into a gas. This vapor had nowhere to go, so it was forced to penetrate the solid copper, atom by atom, until the entire piece was transformed into golden brass from the inside out. It was alchemy in the truest sense, a solid metal breathing in a ghost to become something new and beautiful. This was a profound manipulation of states of matter, turning a solid into a gas to create a new solid, all within the confines of a simple clay pot. They were harnessing vapor pressure, a concept that would not be formally understood for over 1,000 years, through sheer practical genius. A similar, yet even more dangerous, dance was performed with mercury. This liquid metal, shimmering and heavy in its jar, presented a different kind of opportunity. Artisans discovered they could dissolve gold or silver into mercury, creating a thick, silvery paste known as an amalgam. This paste could be brushed onto a statue, a piece of jewelry, or even the ceilings of a palace, adhering to the surface in a way that pure gold leaf never could. Then came the most perilous part of the operation. The object was gently heated, just enough to make the mercury boil away as a toxic, invisible vapor, leaving behind a perfect, seamless, and permanent layer of pure gold. This fire gilding technique produced breathtaking results, but the cost was immense. The mercury fumes were a slow, insidious poison, attacking the nervous systems of the gilders and often leading to madness and a painful death. These artisans were not just craftsmen, they were experimental chemists operating on the very edge of survival. They possessed a tactile, life and death understanding of material behavior that our modern safety protocols and theoretical frameworks have largely replaced. They knew that to capture the beauty of gold, they first had to tame a metallic ghost, and they paid for that knowledge with their health. Their legacy is a testament to the terrifying, clever, and often tragic lengths humanity would go to master the unruly elements of the physical world. That same protective skin is not the only miracle of the Delhi pillar. To stand for 16 centuries, it first had to be born, and its creation was a feat of colossal strength and coordination. This is not a structure built from stacked blocks or riveted plates. The entire 23-foot-tall, 6-ton monolith was hammered into existence from a single, welded mass of iron. Just picture the sheer physical challenge. Ancient Indian smiths did not have electric arc furnaces that could melt tons of metal at once. Their raw material was sponge iron, a porous, crumbly substance produced in small, village-sized clay furnaces. To create the pillar, they would have had to first produce countless individual lumps of this iron, then gather them while still glowing hot, and fuse them into one continuous piece. This technique is known as forge welding, and performing it on such a scale is almost unimaginable. It required a team of smiths working in perfect rhythm, heating sections of the iron to a precise, bright yellow heat, a temperature they judged by eye alone. At just the right moment, they would sprinkle a secret fluxing agent, perhaps a powder of crushed seashells or specific herbs, to cleanse the metal's surface and prevent oxidation. Then, with massive, synchronized swings of their heavy hammers, they would beat the glowing pieces together. The force had to be immense, driving the individual crystalline structures of the separate iron lumps to interlock and merge into a single, unified grain. One miscalculation, one section cooled just a fraction too much, and the weld would fail, creating a hidden seam of weakness that would have torn the pillar apart over time. Yet, modern non-destructive tests reveal no such seams. The entire structure is homogeneous, a testament to a flawless, monumental weld achieved with nothing but fire, muscle, and a deeply ingrained, unwritten knowledge of the metal's behavior. We can build larger things today, but we do so with cranes, lasers, and robotic welders. The Iron Pillar of Delhi stands as a monument to a different kind of power, a symphony of human skill conducted on an anvil of epic proportions. It forces us to wonder what other impossible feats of fabrication were once commonplace, their methods now silent in the unrecorded rhythm of 1,000 forgotten hammers. The scene must have been one of controlled chaos and immense physical strain. Picture a team of master smiths, their faces illuminated by the hellish glow of multiple forges, coordinating their movements with a wordless precision. Their task was to heat individual chunks of iron, each the size of a large loaf of bread, to a precise, bright yellow welding heat. Judging this temperature by eye alone was the first critical test. A section too cool would not fuse, one too hot would burn and become brittle. At the exact moment, they would sprinkle a secret flux, perhaps borax or crushed seashells, onto the glowing surfaces. This agent acted like a magical cleaner, bubbling away impurities and creating a pristine surface for the atomic bonds of the iron to merge. Then, with a synchronized, thunderous rhythm, their heavy hammers would fall. The force was not about brute strength alone, but about precise impact, driving the crystalline structures of the separate iron pieces to interlock and become one. This was not a single event, but a painstaking, days-long ballet of heat and force, building the pillar layer by welded layer. A single miscalculation, one hammer blow on a piece that had cooled a fraction of a degree too much, would create an invisible seam of weakness. Over centuries, that hidden flaw would have acted like a perforated line, allowing corrosion and stress to tear the monolith apart. Yet the pillar stands seamless. This success speaks to more than just individual skill. It reveals an astonishing level of social organization. This was a project that required the synchronized labor of an entire community of experts, from the miners and charcoal burners to the fire tenders and the master smiths who directed the entire operation. Their empirical understanding of iron's behavior was a form of collective genius, a knowledge written not in books but in the shared rhythm of their hammers and the communal reading of the fire. This large-scale metalworking knowledge was a product of its specific cultural and technological moment. When that moment passed, when the dynasties that sponsored such projects fell, and the guilds that held the secrets dispersed, this profound, hands-on understanding of massive forge welding simply faded from memory. The pillar remains a solitary giant whose very existence asks a haunting question. How many other grand techniques have vanished because the community that sustained them was lost? Even the stars were once seen through a metal we can no longer perfectly cast. Centuries after the great bronze mirrors of China, another reflective alloy emerged to unlock the heavens. This was speculum metal, a brilliant, brittle blend of copper and tin, sometimes laced with arsenic, that became the heart of the world's most powerful telescopes for over 200 years. Its creation was a battle against the very nature of the material. To serve as a telescope mirror, a disk of speculum had to be a masterpiece of homogeneity. The molten alloy had to cool with perfect uniformity, without a single hidden bubble or internal flaw, for any imperfection would warp the mirror's shape under the stress of polishing and distort the light from distant stars. The greatest triumphs of this art were the massive mirrors cast by astronomers like William Herschel. With them, he discovered the planet Uranus and mapped the depths of the Milky Way, his gaze powered by a man-made alloy of unparalleled reflectivity. Yet, the very process of creating these mirrors was a kind of alchemy. The exact recipes for the metal varied from workshop to workshop, a secret balance of copper and tin that maximized brilliance without inviting brittleness. The polishing technique was even more elusive, using a series of increasingly fine abrasives from emery to rouge. A craftsman would spend weeks grinding the mirror's surface, not to a simple curve but to a perfect parabolic shape. This was a task performed by hand and eye, a delicate dance of pressure and patience that could be ruined by a single moment of miscalculation. The mirror was not merely polished, it was brought to life, its surface transformed into a perfect, silent eye to the cosmos. Then, in the 19th century, a better technology arrived. Scientists discovered how to coat glass with a thin, reflective layer of silver. Silvered glass mirrors were lighter, easier to cast, and could be recoated when they tarnished, unlike solid speculum metal which had to be laboriously repolished. The switch was immediate and total. The art of casting and polishing speculum metal, a craft that had taken generations to refine, became obsolete overnight. The workshops fell silent, the master polishers took up other trades, and their unwritten knowledge vanished within a single generation. This is a different kind of loss, one born not from the collapse of an empire, but from the relentless march of progress itself. We gained a superior tool for astronomy, but we paid for it with the complete extinction of a magnificent and difficult craft. The great speculum mirrors that still exist are more than historical artifacts. They are monuments to a forgotten expertise, a silent question written in polished metal. What other profound skills have we willingly traded away in our pursuit of the new? That final, flawless polish was a slow and silent dialogue between the artisan and the metal. For days on end, the craftsman would work the mirror's surface with a series of specially prepared rouge compounds, each one finer than the last. His touch had to be impossibly light and perfectly even. Too much pressure in one spot would create a minute flat area, distorting the parabolic curve that was essential for gathering starlight without aberration. The wrong stroke could leave a hair-thin scratch, a permanent flaw that would scatter light and blur the image of a distant nebula. This was not a mechanical process, it was a form of meditation. The master polisher read the metal through his fingertips, sensing the subtle changes in drag and friction that told him the surface was approaching perfection. He worked by intuition honed over a lifetime, a black art where the only textbook was experience and the only valid test was the crispness of a star's image. This profound tactile knowledge died with the last of these specialists. When silvered glass mirrors arrived, they were a revolution in practicality. A tarnished glass mirror could be stripped and recoated with relative ease, but a tarnished speculum metal mirror required its entire surface to be laboriously repolished by a master, a costly and time-consuming ordeal. The new technology made astronomy more accessible, but it severed the vital link of apprenticeship. Why would a young artisan spend years mastering the elusive skill of polishing speculum when the world had moved on? The knowledge was not stolen or destroyed. It was simply allowed to fade away, no longer relevant in a new technological paradigm. We have the old recipes for the rouge. We have the documented accounts of the polishing strokes, but we have lost the living feel of the craft, the unwritten sensory feedback that guided the master's hands. We possess the map, but we can no longer walk the path. The perfect mirror required more than a formula. It demanded the hand of a master, and that is a resource that cannot be replicated in any laboratory. The shimmering surface of a fire-gilded statue hides a terrifying secret. To achieve that perfect, seamless layer of gold, ancient artisans first had to tame a liquid metal that defied control. They would take their pure gold and dissolve it into a bath of shimmering, silvery mercury, stirring the mixture until it formed a thick, pasty amalgam. This paste could be brushed onto almost any surface, clinging to intricate details where fragile gold leaf would tear. Then came the moment of truth. The object was placed over a gentle heat, not enough to melt the gold, but just enough to make the mercury boil away. As the temperature rose, the mercury would vaporize, rising from the surface in an invisible, deadly fog, leaving behind only the pure, brilliant gold, perfectly bonded to the object beneath. The result was a gilding of unmatched durability and beauty, a metallic skin that seemed to have grown there naturally. Modern electroplating, where an electric current pulls gold ions onto a surface, can create a similar look, but it often lacks the same deep, warm luster and can peel or wear unevenly over time. The fire-gilded surface, born from vapor and heat, was a part of the object itself, but this beauty came at a horrific price. The process filled the workshop with toxic mercury vapor. The artisans breathing this invisible poison day after day would slowly succumb to its effects, suffering from shaking hands, mental deterioration, and a slow, painful death. They were walking a razor's edge, balancing the perfect temperature to drive off the mercury without overheating the gold or the object, all while being slowly poisoned by their own craft. The theory is simple to us now, a basic lesson in chemistry, but the master's art was in the subtle, unwritten details. How did they prepare the amalgam to the exact right consistency? What was the precise, gradual heating cycle that prevented the gold from bubbling or blistering as the mercury fled? How did they judge the airflow in the room to carry the deadly vapor away without cooling the object too quickly? These were the tricks of the trade, the sensory knowledge that lived in the hands and lungs of the artisans, a deadly dance of fire and vapor that produced miracles of art at the ultimate cost. That knowledge is gone now, sacrificed to the very poison that made the miracle possible, leaving behind only the silent, golden glow of its beautiful, lethal legacy. That golden glow on a medieval reliquary or a serene Buddhist statue came with an invisible receipt, a bill paid not in coin but in human life. The artisans who mastered mercury gilding achieved a level of beauty and durability we still admire, yet their workshops were chambers of slow, invisible poison. This presents us with a profound and unsettling dilemma. Is the loss of this knowledge a tragedy or a form of progress? We rightly mourn the forgotten formulas for resilient concrete and unbreakable steel, technologies that could have built a better world. But what do we do with a technique that created magnificent art through what was essentially institutionalized poisoning? The loss of mercury gilding is not a clear-cut case of a dark age descending. It is a story with two faces. On one hand, a brilliant tactile skill has vanished from the world, a method of bonding metal to metal with unparalleled finesse. On the other, its disappearance represents a moral awakening, a move away from a practice that caused tremors, madness, and an agonizing death for the very people who practiced it. This forces us to ask a difficult question about our quest to reclaim the past. Should we pursue the recovery of all lost knowledge, or are some doors better left closed? The haunting legacy of these gilders compels us to consider the full cost of an artifact, a price measured not just in labor, but in the silent suffering etched into its golden surface. This is the ambiguous shadow cast by our fascination with lost technologies. The drive to recover them often assumes that all ancient knowledge is inherently valuable, a pure expression of human genius. But history is more complicated. It is also a record of dangerous compromises and terrible trade-offs. The glittering surface of a fire-gilded object is a monument to both artistic triumph and profound human cost. To recover the technique without the suffering would be the ideal, but that may be the one secret we can never truly unlock. The real loss we mourn, then, might not be the dangerous skill itself, but the lack of a safer path to the same stunning result. This is the ultimate cautionary tale of the lost metals, a reminder that the price of beauty can sometimes be too high, and that the most profound progress may occasionally look like forgetting. That same intimate, tactile knowledge of the metal's soul was not reserved for legendary swords alone. It lived in the hands of the chainmail maker, an artisan whose workshop echoed with the rhythmic clinking of thousands of iron rings. To create the flexible, protective mesh that guarded knights across Europe, they first had to solve a fundamental problem: how to turn a rigid iron rod into a long, supple, and perfectly uniform wire. The solution was a tool of elegant simplicity and immense physical demand: the draw plate. This was a thick, hardened steel plate pierced with a series of holes, each one slightly smaller than the last. The process began with an iron rod heated and hammered to a rough point. This point was fed through the largest hole in the plate, then gripped with powerful tongs. The wire drawer, bracing themselves, would then pull with their entire body weight, dragging the iron through the constricting hole, stretching and thinning it into a primitive wire. But iron is stubborn. Its work hardens quickly, becoming brittle and likely to snap under the strain. This is where the secret knowledge came in. After each pass through a hole, the wire had to be annealed. It was coiled and heated in a charcoal fire to a specific, critical temperature, one that relaxed the stressed metal crystals without softening the iron too much. The artisan judged this temperature not with a thermometer, but by the wire's color in the dim forge light, a precise shade of cherry red that only years of experience could recognize. He might even feel the residual heat with a cautious hand, sensing the moment it was ready to be quenched in water or oil. This cycle of pulling and heating, was repeated dozens of times for a single length of wire, as it was drawn thinner and thinner through progressively smaller holes. The goal was a wire of perfect consistency, the same diameter and strength from one end to the other, a feat of manual control that our modern machines take for granted. Once drawn, this wire was coiled around a rod and cut, creating thousands of identical rings. Each one of these rings was then meticulously riveted shut with a tiny iron pin, a process repeated for an entire garment that could contain over 20,000 individual links. This was not mass production, it was a meditation in metal. A single hauberk represented months of focused labor, a physical record of one artisan's unerring feel for heat and force. We can manufacture chainmail today, of course, but it is often buttered or welded, lacking the historical authenticity and the resilient, hand-forged integrity of riveted mail. The true loss is not the ability to make wire, but the vast, unwritten library of sensory data that allowed a human being to achieve such flawless consistency through fire, muscle, and an intuitive connection to the iron itself. The wire drawer's hands were his most sensitive instruments. With immense physical strength, he would grip the end of a heated iron rod with his tongs and pull, his entire body braced against the resistance of the draw plate. The iron squealed as it was forced through the hardened steel hole, stretching and thinning into a primitive wire, but this was only the first step in a long and punishing cycle. After each pass, the newly drawn wire, now stiff and brittle from the stress, had to be carefully coiled and returned to the forge. The artisan's true skill was in reading the fire. He watched for that exact shade of cherry red, a color that meant the metal's internal crystals had relaxed just enough to be drawn again without snapping. A fraction too cool and the wire would break, wasting hours of labor. A moment too hot and the iron would become too soft, losing the essential strength needed for armor. This intimate dance of pull and heat, repeated dozens of times for a single strand, was what transformed a lumpish rod into a length of wire with perfect uniformity. The quality of the final mail, the legendary chainmail that protected knights for centuries, depended entirely on this foundational process. Every one of the 20,000 rings in a single hauberk began its life under the wire drawer's exacting eye and steadfast pull. The relentless hum of iron sliding through steel was not just the sound of a workshop, it was the sound of an entire army being patiently clothed, ring by meticulous ring, in a flexible skin of iron. This was a fundamental industrial process, the very backbone of medieval warfare, yet its execution remained a deeply personal and almost meditative skill. The wire drawer did not just make a component, he breathed consistency and resilience into the metal itself, a quiet mastery that has been rendered silent by the whir of modern machinery. The deep blue sheen on an ancient Persian dagger is not a trick of the light. It is a whisper from the earth itself, a delicate skin of corrosion that modern science cannot convincingly fake. This distinctive blue or purple patina, found on artifacts from Mesopotamia and Persia, is not a layer of paint or enamel. It is the metal's own story, written in a thin, stable film of magnetite and other complex iron oxides that formed over centuries under very specific burial conditions. This is the opposite of destructive rust. This is a protective, almost artistic transformation. While we can analyze this blue layer down to its atomic structure, we cannot reliably command its formation in a laboratory. The exact slow-motion chemistry between the specific alloy of the steel, the precise pH of the soil, the subtle electrical currents in the ground, and the patient passage of time creates a perfect storm of preservation and beauty. It was likely an accidental gift from the environment, a happy accident of decay that somehow stopped short of destruction. Yet, the consistent appearance of this blue sheen on high-status artifacts suggests that ancient cultures did more than just accept it. They may have learned to read it as a sign of quality, a natural seal of approval from the earth. Perhaps they even developed burial practices or finishing techniques that gently encouraged its growth, a way of asking the world to bless their finest works with this enduring celestial color. The true mystery is not the chemical formula, but the lost conversation between the artisan and the elements. They understood on an intuitive level that a metal's life did not end at the forge. It began a long, slow dialogue with the world, and the most beautiful response was this silent blue song. That celestial blue on a Persian dagger is a perfect scar, a beautiful mark of a long conversation with the earth. But this was not always a sign of neglect. In many ancient cultures, such a patina was not just tolerated, it was actively desired, a final, living finish applied by time itself. The rich green of aged bronze, the deep black of treated silver, the subtle russet of iron, these were not flaws to be polished away. They were valued as signs of wisdom, of ritual use, and of a beauty that could only be earned. The ancient artisan did not see his work as complete when it left the forge. He saw it as a seed, planted with the intention that it would grow into its final, perfect form through years of handling, offering, or exposure to the elements. This required a profound and subtle knowledge, the art of controlled corrosion. They learned to coax the metal's surface using specific chemical baths, smoke, or repeated applications of oils and acids to encourage the growth of a stable, attractive patina. A bronze statue might be treated with vinegar and salt to initiate a uniform green verdigris, a process that mimicked decades of exposure in a single afternoon. A silver amulet could be blackened with sulfur compounds, not to tarnish it, but to make its intricate carvings stand out in stark, sacred contrast. This was a partnership with chemistry, a way of convincing the metal to tell a story before it had even lived one. Modern conservation fights a constant battle against time, aiming to freeze an object in a single, pristine moment. We encase artifacts in argon gas and control humidity with desperate precision, trying to halt the very processes that the original creators might have set in motion. The ancient approach was the opposite. It was an embrace of change, a philosophical acceptance that all things transform, and that this transformation could be guided toward a state of grace. Their metal was not a dead, static object. It was a living, evolving entity, and its changing skin was a testament to its journey through the world. The loss of this knowledge is more than just a forgotten recipe for a green paint. It is the loss of an entire aesthetic, a way of seeing beauty not as a fixed point, but as a continuous, dignified dance with decay. We are left with objects we can only preserve, while their makers left us objects that were designed to mature. That same philosophy of intelligent deception, of making a little precious metal go a very long way, reached its zenith in the golden workshops of the ancient Americas. There, master metalsmiths performed a kind of alchemical magic on an alloy they called tumbaga. This was not pure gold, but a blend of gold and copper, sometimes with a little silver mixed in. In its raw, cast state, tumbaga had a warm, rosy, or even a brassy appearance, a far cry from the radiant yellow of the sun god it was meant to honor. But these artisans possessed a secret that allowed them to cheat the eye and the economy. They knew how to make a surface of solid gold bloom from an object that was mostly copper. The process began after the object was cast and polished. The smith would carefully rub the surface with acidic juices derived from specific local plants. We know these likely included sour fruits or saps with natural citric or oxalic acid. This acidic bath was not a simple wash, it was a precise chemical reaction. The acid would selectively attack the copper atoms on the surface, dissolving them away and leaving behind a porous, spongy layer of pure gold. But this delicate, gold-rich skin was fragile, like a microscopic honeycomb. The true genius of the technique, a step now lost to us, was how they then consolidated this layer. They would repeatedly heat the object in a controlled fire and burnish it with a smooth stone. This heating and hammering would collapse the porous structure, driving the pure gold atoms together to form a solid, continuous, and brilliantly shiny surface of 24-karat gold. The final object looked and felt like it was made from the most precious solid gold, yet its core was a much stronger and more economical alloy. The specific plants that provided the perfect, gentle acidity, the exact number of cycles of acid treatment and heat, and the precise temperature that fused the gold without melting the copper beneath, these were the guarded secrets of the guild. Modern attempts often produce a surface that is too thin and wears away, or one that is blotchy and uneven. The ancient method created a golden shell so perfect and so durable that many of these objects still gleam today, their copper hearts a secret hidden for millennia beneath a perfect golden sun. That golden shell was a masterpiece of surface chemistry. The artisans achieved this miracle through a process we now call depletion gilding, a kind of reverse alchemy that turned a common alloy into a precious metal skin. They began by submerging the polished tumbaga object into a bath of acidic liquid, likely made from fermented fruits like pineapple or sour citrus. This was not a simple cleaning solution, it was a carefully prepared chemical agent. The acid worked with remarkable selectivity, seeking out and dissolving the copper atoms from the very surface of the metal. Copper is far more reactive than gold, so the acid eagerly pulled it into solution, leaving the inert gold atoms behind. But these gold atoms were not a solid sheet yet. They were a delicate, microscopic sponge, a lattice of pure gold filled with empty spaces where the copper used to be. This left the object with a surface that was rich in gold but also fragile and dull. The true artistry came next. The artisan would meticulously heat the object and then burnish it with a smooth, hard stone. This combination of heat and pressure was the final, crucial step. The energy from the heat allowed the isolated gold atoms to migrate and bond together, while the relentless rubbing of the burnisher collapsed the porous structure, compacting it into a solid, continuous, and brilliantly reflective layer of pure gold. The entire procedure was a breathtakingly sophisticated electrochemical process managed with nothing but natural materials and keen observation. They were effectively plating the object with gold, not using electricity like we do today, but using chemistry itself. The master's secret was in the timing. Leaving the object in the acid for too short a time would result in a thin, patchy layer of gold that would wear away quickly. But leaving it for too long would allow the acid to eat too deep, dissolving so much copper that the entire structural integrity of the object was compromised, making it brittle and prone to breaking. The artisan had to know by sight and by feel the exact moment to pull the piece from the bath, a decision that balanced dazzling beauty against fundamental strength. This was not a crude trick, it was a high-stakes dance with corrosion, where the artisan convinced nature itself to paint a perfect golden lie. The quenching bath was where a sword was truly born, its final character decided in a violent hiss of steam. While Damascus Steel captured the imagination with its watery patterns, the armories of Saladin's era produced blades of legendary resilience through a different kind of magic, one performed not in the Crucible but in the tempering forge. These swords, wielded by the Ayyubid warriors who faced the Crusaders, were celebrated for a paradoxical quality. They possessed a razor edge that could withstand brutal impacts without chipping, yet their spines remained flexible enough to bend and return true. This was no accident of chemistry. It was the result of a meticulously controlled thermal dance known as differential hardening. The master smith would heat the entire blade until it glowed a uniform cherry red. Then, with a steady hand, he would quench only the cutting edge, plunging it into a carefully chosen liquid while the spine of the blade remained exposed to the air. The edge cooled almost instantly, transformed into an extremely hard crystalline structure called martensite. Meanwhile, the spine, cooling slowly, retained a softer, more ductile perlitic structure. This created a blade that was, in effect, two different metals fused into one, a hard, glassy edge married to a resilient, springy core. The choice of quenching medium was the smith's most guarded secret. Water produced the hardest edge, but it also risked creating micro-fissures and warping the blade from the thermal shock. Oil provided a gentler quench, reducing stress and the chance of cracking. Some historical accounts even suggest the use of brine or specific animal urines, liquids whose unique salt and mineral content could alter the cooling rate in subtle, beneficial ways. The master knew his steel's soul, and he chose its baptismal fluid accordingly, but the process was not over. A blade fresh from the quench was as hard as it was brittle. To relieve these internal stresses and introduce a measure of toughness, the smith would then temper it. He would gently reheat the entire blade to a specific, low temperature, often judging the perfect heat by the color of the oxide layer that formed on the steel's surface. A pale straw color indicated a perfect temper for a sword's edge, hard yet resilient. A blue tint meant a softer, more flexible state suitable for springs or the blade's spine. This entire sequence, from the selective quench to the color-based tempering, was a symphony of invisible transformations. The smith was not just a blacksmith, he was a master of phase transitions, manipulating the very crystalline architecture of the metal with fire and intuition. He possessed a sensory map of heat and time that no written formula could ever capture. We can replicate the physics in a laboratory with digital controllers and calibrated baths, but we have lost the artisan's intimate conversation with the steel, the ability to read its needs in the shimmer of its heated surface and the sound of its sizzling baptism. The true secret of Saladin's steel was not in its ore, but in the master's breath on the coals and his unerring eye for the color of perfection. The master smith's choice of quenching liquid was a decision of profound consequence. He knew that different mediums pulled heat from the glowing steel at wildly different speeds, and this rate of cooling dictated the very soul of the blade. Dunking the red-hot metal into water created a violent, explosive cooling. This rapid heat extraction forced the iron's internal crystal structure to transform into an extremely hard form called martensite, giving the sword a legendary, razor-sharp edge. But this speed came with a terrible risk. The intense thermal shock could warp the slender blade or, even worse, seed it with invisible micro-cracks, fragile lines of weakness that could cause it to shatter in a knight's hand at the worst possible moment. A slower quench in oil, by comparison, was a gentler baptism. The oil cooled the steel more gradually, producing a slightly less hard but far tougher metal, one that could absorb the shock of a heavy blow without fracturing. This was the eternal metallurgical trade-off, hardness versus toughness, and the quenching medium was the lever the smith used to balance them. But the ancient masters did not stop at simple water or oil. Their workshops were chemical laboratories. They experimented with brine, salt water that cooled even faster than fresh water due to the formation of a vapor barrier, potentially creating an edge of unparalleled hardness if one could master its volatile nature. They used animal fats and urine, liquids whose specific organic compounds and suspended particles altered the cooling properties in subtle, unpredictable ways. A quench in stale horse urine, for instance, might produce a different result than one in sheep's milk, each imparting its own unique signature of stress and strength into the steel. This was not superstition, it was raw experimental science, the perfect quenchant for a specific batch of steel for a specific sword design was a secret as valuable as the ore itself, a piece of knowledge passed from a master to his most trusted apprentice in a whisper. We can analyze 1,000 ancient blades and understand the crystalline structures within them. We can replicate the quenching process in a lab with perfect temperature control. But we can never climb inside the mind of the master smith at that critical moment. We cannot feel his intuition as he judged the color of the heat, the thickness of the blade, and the character of the steel, finally reaching for one particular barrel over another. The quench was the final, irrevocable act of creation, the point of no return where the metal's potential was forged into its permanent identity. In that violent hiss of steam and smoke, the sword's soul was set forever. The final, irrevocable act of creation for a sword lay in its quenching bath, a violent baptism of heat and liquid that set its soul forever. But in the silent, patient space of a bell foundry, an entirely different kind of soul was being coaxed from molten metal. Here, artisans were not forging a weapon of war, but casting a voice for the heavens. The great bronze bells of ancient China and Korea were not merely struck, they were sung, their voices a deep, resonant tone that could carry for miles across mountain valleys, calling the faithful to prayer and marking the passage of time. This was not a simple matter of casting a large piece of bronze into a bell shape. The metal itself had to be tuned. The alloy used, a special high tin bronze known as bell metal, was a precise and unforgiving recipe. It required around 20 to 25% tin, a mixture that made the metal incredibly hard and brittle, but also gave it the necessary rigidity to vibrate with a pure, clean sound. The slightest deviation in this ratio, a single percentage point too much or too little tin, would result in a dull thud instead of a majestic, lingering peal. But the chemical formula was only the first note in a much larger symphony. The true challenge was in the casting. Any tiny bubble of air trapped inside the molten metal, any microscopic impurity, any hidden pocket of stress locked in as the massive bell cooled, would act as a tiny internal damper. These invisible flaws would absorb the vibrational energy, stealing the bell's resonance and shortening its song. The ancient masters developed casting techniques of breathtaking sophistication to prevent this. They built elaborate, multi-part clay molds buried in casting pits, designing intricate channels for the molten bronze to flow in smoothly and evenly, minimizing turbulence that could trap air. The cooling process was a carefully managed ritual, taking days or even weeks, to ensure the metal solidified from the inside out in a perfectly uniform manner, preventing the internal stresses that would deaden its voice. Modern foundries can cast bells of this alloy, but they often struggle to match the acoustic purity of the ancient masters. We can analyze the bronze with spectrometers and know its exact composition, but we lack their profound, unwritten understanding of the relationship between the metal's microscopic crystalline structure and the sound it produces. They knew how to create a metal that was not just a static object, but a resonant body, its entire molecular architecture designed to carry a single, perfect note across centuries. When the great bell was finally raised and struck for the first time, its voice was the sound of the metal's soul, a testament to a craft that understood that true artistry lies not just in shaping matter, but in teaching it how to sing. That resonant bronze voice began not in the foundry, but in the earth. The founders first had to build the bell's negative image, a colossal clay mold built in layers around a precisely shaped core. The outermost layer, the cope, was sculpted with painstaking care, its interior contour defining the bell's final shape and thickness. This was not a rough approximation. It was a masterwork of pottery, for the slightest asymmetry in the mold would become a fatal flaw in the bell's tone. Once the mold was baked hard, the moment of truth arrived. The molten bell metal, a seething river of copper and tin, was poured into the narrow gap between the core and the cope. The founders held their breath, for the metal had to fill this space completely and uniformly without a single bubble or cold shut, a seam where the metal failed to fuse. Any such imperfection would act as a crack in the bell's sonic soul, a dead spot that would steal its voice. Then came the most critical phase, the cooling. This was not a passive wait, but an actively managed process that could take weeks. If the massive casting cooled too quickly, the different sections would contract at different rates, locking in destructive internal stresses. These stresses would not only make the bell prone to cracking, but would dampen its vibrations, muting its song before it was ever heard. The founders controlled the cooling by burying the mold in a pit, letting the earth itself act as a giant insulator, allowing the metal to find its own peaceful equilibrium, solidifying into a stress-free whole. When the mold was finally broken away, the work was still not done. The rough cast bell was a mute instrument. To find its voice, a master tuner would step in. Using hand scrapers and files, he would carefully remove tiny amounts of metal from the bell's inner wall. He was not just shaping, he was listening. As he scraped, he would tap the bell and listen for the complex set of harmonics, the overtone series that gives a great bell its rich, layered voice. He knew that shaving a little from one area would raise the pitch of a specific overtone, while thinning another section would affect a different harmonic. His ear was his only tuner, his hands his only calibrators. He worked until the fundamental note and its overtones existed in perfect, resonant harmony. This was the ultimate synthesis, a process where the founder was simultaneously a geometer, a chemist, and a conductor. The bell's voice was not something added after the fact. It was encoded into its very form, a song written in metal and waiting for the clapper to read it aloud. The loss of this art is not just the loss of a manufacturing technique. It is the silencing of a specific kind of listening, a sensory skill that could hear the potential for a perfect note hidden within a silent, rough cast shell. High in the Andes, the air itself seems to hold a metallic chill, a memory of the brilliant silver that once adorned its temples. The Incas and the cultures that preceded them were not merely miners of the sun's pale metal. They were its masters, weaving silver into the very fabric of their spiritual and political life. They understood that pure silver was often too soft for the grand expressions they envisioned. Their genius lay in creating sophisticated alloys, blending silver with copper for strength, or with gold to create a radiant, pale yellow electrum. But some artifacts defy these simple classifications. A ceremonial knife, a ritual vessel, a royal ornament, these objects possess a unique, almost liquid whiteness, a harder, more resilient sheen than ordinary silver should allow. Modern analysis suggests a startling possibility. These master smiths may have been using elements like arsenic in their alloys. The addition of arsenic, even in tiny amounts, can dramatically whiten the appearance of silver and increase its hardness, creating a metal that was both stunningly beautiful and incredibly durable. This was not a crude craft, it was a precise and subtle art, a deep understanding of how to manipulate the very soul of the metal. Then the world arrived with a different kind of fire. The Spanish conquest was not merely a military invasion, it was a systematic erasure of an entire material culture. The conquistadors saw these magnificent objects not as works of art, not as sacred vessels, not as the culmination of centuries of metallurgical tradition. They saw only bullion, raw material to be melted down into ingots and shipped back to Europe to fuel an empire on the other side of the world. In their furnaces, they did not just melt silver. They melted libraries. Each ornate beaker that was fed into the crucible held within its form the secrets of its alloy, the knowledge of its quenching, the story of its polish. The smiths who knew the precise incantation of heat and arsenic, the elders who understood which ore produced the most resonant silver, the entire living chain of knowledge that stretched back for generations was shattered in a single voracious generation. The loss here is uniquely profound. It is not the mystery of a single formula like Damascus Steel, but the collapse of an entire continent's philosophical approach to metal. We are left with a haunting silence. We can find silver mines, we can analyze the few surviving pieces, but we cannot hear the stories the metal was meant to tell. The true value of Andean silver was never its weight in grams, but the way it captured the light of the high mountain sun, a light that now shines on a history we can only see in fragments. That gleam of Andean silver was a final, fleeting light before a long darkness fell. The arrival of the Spanish conquistadors was not just a clash of empires, it was a collision of worlds with fundamentally different understandings of what metal meant. For the indigenous cultures of the Andes, silver and gold were the sweat of the sun and the tears of the moon, sacred materials woven into their cosmology, their identity, and their art. For the Europeans, they were currency, pure and simple, a measure of wealth to be counted, melted, and shipped. This fundamental disconnect led to one of history's most catastrophic erasures of knowledge. The Spanish did not see the intricate alloy in a ceremonial knife. They saw an inconvenient shape that needed to be reduced to a standard bar. They did not recognize the master smith who could control the flow of arsenic to harden silver. They saw a pair of hands to be enslaved in a mine. The result was a systematic, violent dismantling of an entire technological ecosystem. Countless artifacts, each one a repository of generations of empirical research, were fed into the melting pots. The smiths themselves, the living libraries who held the unwritten secrets of their craft, were killed, displaced, or forced into a brutal new system that had no use for their nuanced artistry. The transmission of knowledge, a delicate chain that had been passed from master to apprentice for over 1,000 years, was severed in a single, brutal generation. We are left with a profound silence. We can only guess at the full range of alloys they perfected, the unique tempering techniques for high-altitude metals, or the symbolic meanings encoded in specific metallic compositions. The loss in the Andes is a stark and sobering lesson. It reminds us that knowledge is not a permanent possession. It is a fragile flame, and it can be extinguished not just by the slow passage of time, but by the deliberate, decisive force of conquest. That same dream of a self-preserving metal was not confined to grand monuments or royal treasures. It lived in the humble taverns and homes of medieval Europe, whispered in legends of a commoner's marvel, never dull pewter. The tankards and plates that filled the cupboards of the Middle Ages were typically made from this tin-based alloy, and they required constant, laborious polishing to keep their bright, silvery sheen. Yet stories persist of a special formulation, a secret pewter that defied this dull fate. These legendary mugs and platters were said to retain their brilliant luster for a lifetime, never needing the abrasive rub of a cloth to shine. Modern pewter, which we know as an alloy of tin with antimony and copper, does slowly oxidize, developing a soft, gray patina over time. So what was the secret of the legendary, never-dull metal? One compelling theory points to a happy accident of composition. It is possible that a specific batch of tin ore, used by a particular guild of pewterers, contained trace amounts of an unexpected element. Perhaps it was a little phosphorus or even arsenic that, when alloyed with the tin, catalyzed the formation of an ultra-thin, transparent, and incredibly stable oxide layer. This would have acted as a permanent shield, much like the Massaoite film on the Iron Pillar of Delhi, protecting the soft metal beneath from the corrosive touch of air and moisture. The pewter would have been passively protected, its beauty sealed in by a microscopic skin of its own creation. Another, more human, explanation is just as plausible. Could the legendary brightness simply have been the result of constant, loving use? A tavern keeper's favorite measuring cup, handled dozens of times a day, would have been perpetually burnished by the natural oils in human hands and the friction of being passed across a wooden counter. A family's prized dinner plate, used for every meal and wiped clean, would have undergone a slow, continuous polishing that no single cleaning could ever match. In this case, the never-dull quality was not a property of the metal itself, but a gift bestowed upon it by the rhythm of daily life. The true mystery may lie in the combination of both, a specific, slightly harder alloy that responded perfectly to this daily caress, developing a hard, brilliant polish that felt like magic. The persistence of this legend speaks to a very modern desire, the quest for a maintenance-free material. We see this same yearning in our own world, with stain-resistant fabrics and self-cleaning glass. The medieval dream of a pewter mug that never needed polishing is the direct ancestor of our own pursuit of convenience and permanence. It reminds us that the wish to escape the drudgery of upkeep, to possess an object that remains eternally new, is a timeless part of the human story. This deep yearning for objects that refuse to fade is a thread woven through all of human history. It is the dream of a world where things do not wear out, where the relentless pull of decay is held at bay by the perfect material. You can see this quest in the alchemist's desperate search for the philosopher's stone, a substance that could not only create gold but also grant immortality. You see it today in our laboratories, where scientists engineer self-healing concrete that can seal its own cracks. The legend of the never-dull pewter tankard is a humble, domestic echo of this grand ambition. It was the medieval housewife's version of eternal life, a wish for a simple mug that would always gleam without the endless, tedious labor of polishing. Whether such a pewter ever truly existed is almost beside the point. Its power lies in the ideal it represents, a North Star that has guided our relationship with matter for millennia. The real tragedy of these lost formulas is not always the loss of the final, perfect product. It is the loss of the countless small discoveries made along the way. Each failed batch of alloy, each accidental addition of a new ore, was a data point in a vast, unwritten experiment. An artisan who stumbled upon a trace of phosphorus that made his pewter shine a little longer had found a crucial clue. He had uncovered a small piece of the puzzle of passive stability, but when that knowledge died with him, the entire path of inquiry was erased. We are left to rediscover those clues from scratch, using billion-dollar microscopes to find what a curious craftsperson might have once held in their hands. Our ancestors were not just primitive technicians, they were fellow travelers on this same eternal journey, using the tools they had to search for a glimpse of permanence in an impermanent world. Their lost metals are not just curiosities, they are signposts from a different road, reminding us that the hunger for perfection is the very engine of discovery. A gleaming tray in an 18th century European drawing room looked for all the world like solid silver, yet it never tarnished. This was Paktong, the mysterious Chinese silver that baffled Western scientists. It was not a mere coating or a cheap imitation, but a sophisticated alloy of copper, nickel, and zinc, a material that Europe had no idea how to make. China's mastery of this metal stretched back centuries, born from a unique convergence of geology and genius. They possessed access to rare nickel ores and, through a process lost to us, learned to smelt this stubborn, refractory metal. Nickel resists separation from its ore, requiring incredibly high temperatures and specific chemical conditions to yield a pure metal. The Chinese metallurgists developed a complex, multi-stage process to achieve this, likely involving repeated roasting and smelting with particular fluxes to isolate the nickel. This was not a single recipe, but an entire school of pyrotechnology, a carefully guarded secret that produced an alloy with a brilliant silver-white luster and a remarkable resistance to corrosion. When trade finally brought Pactong to the West, it was an instant sensation. Here was a material that looked like silver but was far more durable and, strangely, required no polishing. European chemists and industrialists scrambled to reverse engineer it. They could identify the three main metals, but the secret lay in the precise proportions, the specific smelting sequence, and the source of the nickel itself. They were trying to copy a finished book without understanding the language it was written in. The original Chinese methods faded into history, a casualty of shifting trade routes and the exhaustion of the specific nickel mines that supplied the perfect ore. The European factories eventually produced their own version called nickel-silver, but it was a separate invention born of their own industrial methods. The original Pactong, the true Chinese silver, remains a ghost, a testament to a self-contained technological tradition that perfected a metal and then took the secret of its making to the grave. Nickel is a notoriously stubborn metal. It clings to oxygen with a fierce grip, forming a stable oxide that resists all but the most determined efforts to break it free. To isolate pure nickel from its ore, you need more than just a hot fire. You need a carefully engineered environment, a sealed furnace where you can control the very atmosphere, starving the reaction of oxygen while introducing precise chemical agents to coax the metal out of its rocky prison. The ancient Chinese metallurgists who created Pactong mastered this alchemy. They likely used a complex, multi-step process of roasting and re-smelting the ore with specific fluxes, perhaps charcoal or other carbon-rich materials, that would greedily grab the oxygen away from the nickel, reducing it to a pure, usable metal. This was not a simple recipe anyone could follow. It was a localized art born from a perfect storm of unique geology and generations of accumulated experimentation. The knowledge lived and breathed in one specific region, tied to the particular character of the nickel ore pulled from a handful of now forgotten mines. The brilliant, untarnishable white of their Pactong was a direct result of this nickel, an element that bleaches the red out of copper and gives the alloy its signature silvery glow. But this very specialization was its greatest weakness. When those specific mines were exhausted, or when the trade routes that carried the finished Pactong to the world shifted and collapsed, the need for this incredibly difficult process vanished. The masters of the technique had no one to pass their secrets to, and the knowledge confined to such a small pocket of experts simply faded from memory. This is the recurring tragedy of these lost metals. Highly specialized technical knowledge is fragile. It thrives in a specific ecosystem of resources and demand, and when that ecosystem is disrupted, the light goes out, leaving behind only the beautiful, baffling object to testify to a genius that was once briefly alive. A simple bronze brooch clasp, bent open and shut countless times over a lifetime, never breaks. It simply remembers its shape. This quiet miracle of elasticity, found in countless ancient clasps, springs, and tools, reveals a mastery of bronze that goes far beyond simple casting. These artisans were not just shaping metal, they were programming it with memory. To achieve this spring-like quality, they had to solve a complex puzzle of composition and treatment, all without any understanding of the crystalline dance happening within the metal. The first secret was in the recipe. The proportion of tin to copper had to be exquisitely precise. Too little tin, and the bronze would be too soft and malleable, bending easily but staying bent. Too much tin, and the alloy would become hard and brittle, snapping under the slightest stress. The ancient smiths, through generations of trial and error, found that golden ratio likely between 8 and 12% tin, which gave the bronze the perfect balance of strength and flexibility. But the correct alloy was only the beginning. The true magic was in the hands. To make the bronze springy, the smith had to work hard on it. He would repeatedly hammer the cooled metal, compressing and distorting its internal crystal structure. This hammering made the bronze harder and stronger, but it also made it stiff and prone to cracking, like repeatedly bending a paperclip until it snaps. So, at just the right moment, he would stop and anneal the piece. He would heat it gently in his forge, not to a glowing red, but to a specific, lower temperature that would relax the stressed crystals just enough, allowing them to reform into a more resilient, aligned structure without softening the metal completely. This cycle of hammering and heating, of stressing and relieving, was a delicate dance. The smith judged the perfect annealing temperature not with a gauge, but by the faint, subtle colors blooming on the metal surface, a spectrum of knowledge written in heat tints only he could read. He was teaching the bronze to resist permanent change, to absorb energy and then release it, to always return home. This was not a science of formulas, but a tactile art of feel and rhythm. The loss of this specific, hands-on knowledge is why many modern bronze replicas lack that same lively spring. We can analyze the alloy, but we cannot replicate the artisan's intimate conversation with the fire, the precise moment he decided the metal had been stressed enough and was ready to be healed. That bronze clasp holds more than a pin. It holds the ghost of a master's timing, a perfect pause in the rhythm of a hammer that gave a simple metal the gift of memory.